Okay, ladies, so this is what we did today in class. First of all, we just very quickly reviewed the formula for the period of a pendulum. So remember, it's 2 pi root L over G. For the spring, you should have gotten something pretty similar. So you still have that 2 pi factor, but now instead of L and G, what we have is mass and spring constant, okay? So period of spring is 2 pi times the square root of m over k. Then we quickly remembered, back when we were talking about circular motion, the relationship between period and frequency. So remember, they are inverses of each other. So if instead of a period I wanted to find the frequency, all I would do was take 1 over the period. So for a pendulum, it's 1 over 2 pi times the square root of g over L. For spring, it's 1 over 2 pi times root k over m. Okay, so period and frequency still mean the same thing. Period is how long it's going to take for one complete cycle, so for a pendulum back and forth. Frequency is how many cycles per second. Okay, so does it get through a whole back and forth in 1 second or whatever. Frequency is measured in hertz, if you don't remember, and period in seconds. Okay, so then we talked about motion graphs, okay, everyone's favorite topic. So these are the motion graphs for simple harmonic motion. Both the spring and pendulum both obey these motion graphs, okay? So what we notice here when we're talking about displacement, okay, is that it looks like a cosine graph. It is a cosine graph, okay? So if we go real quick and just go to what this looks like, okay, for pendulum, back and forth and back and forth. This is going to be cosine. With my spring, you can actually see it go up and down and up and down, okay? It is exactly what you're thinking of, just up and down, regular old cosine for math. So for the equation of my displacement, what did I end up getting is x of t, so my position with respect to time, equals x max times the cosine of omega t. Now, x max, all it is my maximum displacement, okay, or my amplitude, okay, times the cosine of omega t. Now, omega, if you remember from angular momentum, or excuse me, angular motion, omega was our angular velocity. This is angular frequency. It's very similar, but slightly different. Angular frequency is just the magnitude of our angular velocity. So I don't care about direction, okay? It's just looking at that speed. If I want to put it in math terms, if you remember, V equals R omega, but we also know that V equals 2 pi R over the period. Putting those two equations together, I can get omega equals 2 pi over the period. Okay, remember capital T is for period. So that omega, that angular frequency, okay, is still radians per second. Okay, we're going to treat it very similarly, okay, but it's 2 pi times period, or we could just do 2 pi times the frequency. Okay, so all of these equations, okay, mean the same thing. Okay, so if I'm just looking at my graphs, we have displacement, so cosine. To get velocity, what you have to remember is that it's the slope of my line at any given point, or the derivative. So for those of you in calculus, it's a derivative. And if I have cosine, when I go from cosine to sine, okay, there's the answer. When I take the derivative of cosine, I actually get negative sine. Okay, when I take that derivative again to get acceleration, I have a negative cosine graph. Okay, so if we look at the displacement and acceleration graphs, they're very similar, they're just opposite. Okay, so when my displacement is at its maximum, okay, so right here, my acceleration is at its maximum in the negative direction. Okay, so some things to note right here. Velocity is 0 when displacement is largest. Okay, so when the displacement is biggest, it's not moving. Okay, another thing, acceleration is going to be biggest when velocity is 0. Okay, so if we go back to our pendulum, just notice displacement is biggest right now, okay, right at that edge. What's happening is all of the energy, okay, is all potential at the highest point, Okay, so when that displacement's the biggest is when my velocity is 0, there is no kinetic energy. At that equilibrium, so right when it's in that middle, the displacement is 0, so I don't have any potential energy. What I have instead, it's all kinetic. Okay, so we have to kind of think of it in terms of energy as well. So potential to kinetic to potential again. Same thing happens with a spring. Okay, when it's maximally stretched or compressed, okay, that's when potential energy is the biggest. When it's at that equilibrium point is when kinetic energy is 0. Okay, so here we go right here. Just things with energy to remember. When we talk about springs, my potential energy of a spring is 1/2 kx squared. Okay, don't forget that one. We are going to need it in this unit. So big things to note, okay, is we've done a lot of this before. Okay, we've already talked about periods. We've already talked about frequencies. We've already talked about omega. We've talked about energy. Okay, we've talked about motion graphs. It's just kind of putting this all together now and putting it, like looking at it in a different way. Okay, so we did talk about all of this. The packet that you all picked up, okay, is homework. I want you guys to try your best. A lot of it is review from previous units, so do what you can on this one, okay? And if you have questions, just let me know.